I am delighted to welcome the fellows and visitors to the second discussion meeting of the 2025 session. This session is being sponsored by the medical section of the Royal Statistical Society, and we'll be discussing the paper New Tools for Network Time series with an application to COVID-19 hospitalizations by Nason et al. With grateful thanks to Imperial College London, this Royal Statistical Society discussion meeting is being held here, where it also welcomes an online audience. Please keep your microphones muted and cameras turned off unless called to speak during the open session later. A recording of the meeting will be posted on the RSS YouTube channel. If anyone prefers not to be filmed, you will have to let us know and we can edit that part out. For those online, if you experience any technical problems, please use the chat box, and so our technical team will be able to help you as soon as they can. We actively encourage everyone to contribute to the discussion of the paper in the open session later. Comments and questions can be brief or up to 5 minutes. Anyone who has given their name in advance will be called first. All comments can be written afterwards, a maximum of 400 words, and will be published in the journal Series A along with the paper. So do you have any questions at this point? So now we move on then to the presentation of the New Tools for Network Time series with an application to COVID-19 hospitalizations by Nason and the other co-authors. So the paper will be presented by Guy, Nason, and co-authors Mario Borgia Cortino and Daniel Salnikov, and it will publish in the Journal of the Royal Statistical Society Series A in 2026. I'd now like to call on Guy to present the paper. Thank you.
Okay, good afternoon, everybody. Thank you for coming, whether here or online. Thank you very much to the medical section for hosting this, for which we're very grateful. And also thank you to the Royal Statistical Society entire editorial team who are working on this, because you worked really hard and there was lots to do. So thank you very much for all your help on this. I'm obviously pleased to be joined by Daniel Salnikov and Mario Cortina Borga, who are my fellow co-authors on this paper. So I'd like to just make a start on what we're here to talk about, which is these new tools for network time series with an application to COVID-19 hospitalizations. And I guess the emphasis here is on new tools. So okay, I might have to use the mouse to advance. So let me give you a little bit of an introduction. So we are first going to talk about what kind of data we're going to be looking at, the kinds of problems that we're going to be analyzing. And then after that, we're going to talk about some models that we're going to use for these network time series, which we're going to introduce in the first part. And then we're going to lead on to the new tools that we mentioned in the title. So these are the network partial autocorrelation, the network autocorrelation, and the associated Corbit plots. So if you like, one of the main innovations here are the Corbit plots, which is a way in which we can visualize what's going on in the partial autocorrelation and autocorrelation structure on their own, but also with respect to other covariates or through time. And in fact, we're going to use a variant of the Corbit plot called the R-Corbit plots to do this. And in the paper, there's some other things, some other tools. We're going to focus on one of those because of time, and that's this concept of a global relevance index. And at the end, I've put that we've got an application to the COVID-19 mechanical ventilation beds. But to be honest, we're going to be looking at this time series kind of from the start and, as we go through the talk. So it's not just going to come at the end. Okay. So let me start with the data. I think that's the best place for us statisticians to start. And the data set that we're going to be focusing on in this presentation and in the paper are the number of patients occupying mechanical ventilation beds prevalence during the pandemic for 452 days at 140 English NHS trusts between April 2020 and July 2021. English, because I think if you remember the pandemic, we have 4 countries and they all kind of did their own thing with respect to data, which is maybe slightly annoying, but there are obviously reasons for that. The other thing to say is this was one of the data sets that you could get from the COVID dashboard, which if you remember when the COVID dashboard started, it was fairly simple. And then more and more data sets came on and it grew and it grew and it grew. And they were collecting data on all kinds of things. And it was during this period that we collected this. One of the referees quite rightly said, well, can we get some more data? And the answer is, well, it's gone now. So they don't actually collect this anymore. They collect other COVID things still, but not this. And we are going to call this particular data set X tilde IT, again, for the 140 English trusts and 452 daily time periods. And I know that notation is a bit cumbersome, but we're going to dump it in a minute and focus on a transformed version, which we'll call something else. I'm sure most people here know what an NHS trust is. I'm not sure I fully understand what an NHS trust is, but a very simple way of saying what it is it's a local health system. It's usually a collection of maybe 1, 2, 3, 5 hospitals. Occasionally, some of those could be specialists, eye or children or something. But the way in which they collected this data was on a per trust basis. Sometimes that was one hospital putting people onto mechanical ventilation beds. Sometimes it was two or 3 bigger ones in the big city areas. So effectively, coming from my tradition of time series, we have a multivariate time series here of dimension 452 times 140, which is about 63,000 observations altogether, which sounds like a lot of data, and in some sense it is. I should say that the X tilde observations, they're count data, so we shouldn't or can't use kind of regular linear models directly on those, which are really designed for more symmetric and more continuous like variables. So in time-ordered fashion, we operate on X IT. That's the notation that we're going to use really from now on, which is just a simple log of 1 plus X tilde transformation. Probably we should be using more specialized models, such as the Poisson network autoregression, lovely model introduced by Armelotta and Fokianis in 2023, which is probably a bit after when we first started working on this paper. But there are ways of kind of extending what we did or altering it to make use of those kinds of models. I think it's very important to look at the data. I've got 2 univariate time series here out of the 140 trusts. On the one on the left is Imperial College Healthcare NHS Trust. That's not the same as Imperial College London. So the trust and the university are different things, but they are linked because you get medics working in kind of both. You can see clearly this is the start of the pandemic. This is November, roughly 2021 at the end. And then you have like the first initial wave, the second wave. And it's not very clear here, but it is on this one, the so-called third wave, which was a bit less. And the one on the right is University Hospitals Birmingham Trust. And you can see that the numbers there were worse. And that doesn't necessarily mean it was worse in Birmingham. It probably means that there were just more people going to that Birmingham hospital, whereas in London there's more of a choice of where people go. Okay. And that was count data. This is the transformed time series. And this is just to show you what it looks like. Again, it's not particularly perfect because you have these slightly strange artifacts here that the Poisson network models will probably handle a lot better. But it's certainly giving us a bit more of a symmetric distribution to play with. And again, if you're a time series person, you'd want to look at things like autocorrelation, cross-correlation, and here is just the version of that for these 2 time series. And sure enough, you can see there's a lot of autocorrelation, and there's a lot of cross correlation. So it looks like something like an autoregression. That kind of model would be a suitable thing. You know, it's a perfectly good idea to start looking at this data with these kinds of models. And, you know, similar things happen for the other variables as well. But of course, remember, with 140 time series, there's going to be a lot of pairs in that. So it's quite a complex thing to look at if you're looking at all those pairs. And in fact, you know, I defy anyone to look through, what would be 140 choose 2, which is probably about 4,000 or something, pairs to look at, which is rather a lot. So what we decided to switch to was something called network time series. As I said, we're coming from the network time series, we're coming from the time series direction. And the idea here is that if you have some big multivariate time series, many dimensions, what you try and do is associate that with a network or a graph. And there are lots of ways in which you can do that for this kind of data. You could possibly link with people movement, especially if you know a lot about what the transport corridors are, where people go, that kind of thing. You could link by weather patterns. So, for example, wind-borne dispersal of disease vectors might be something you want to look at. Obviously not in this case, but we have another data set with foot and mouth where that is actually an issue. But we're basically here using a basic geographical link. And what we do is, for this particular data set, we use something very simple, which is a minimal spanning tree. We have all of the centroids, if you like, of the trusts. We know where their kind of center value is, which is based on a slightly rough approximation to where the kind of actual center is, but it's good enough for what we want. And then we form a minimal spanning tree amongst all of those 140 trusts. But then what we say is, that's a very sparse thing, the minimal spanning tree. We say we're going to augment that with what we called closed trust geolinks. So we actually link two trusts if they're 120 kilometers apart from each other or less. Okay, and you may say, where did 120 kilometers come from? In fact, the referee said that quite rightly. And you can look in the paper for a description of how we did that. But basically, we tried lots of distances, and we chose the one that enabled us to forecast what was going on with it in the series the best. So it's like a predictive method for trying to choose a good distance away. Okay. As well as edges, we have the distances between the trusts that we link, which we also make use of. And here's the network that we come up with, which you'll probably say, gosh, it looks a bit crazy, and it kind of does. So clearly in these areas here, so here's London, here's the northwest of England. Within there's quite a lot of trusts and a lot of links going on. But you've also got trusts right down here. So this is in the far southwest in Cornwall, that's Truro, and then RNN is North Cumbria. Okay, and so not only are these kind of further away, but they don't have as many links with the rest of the trusts. But that's the network that we used as the basis for our analysis. So we've got a multivariate time series. We've got a network that we like the look of. Again, it's not the only one we could try, or indeed did try. But the key aim here is to focus on simple models. Because if you remember what I said, first of all, looking at that cross-correlation plot, there are 140 choose 2 possible pairs, and a vector autoregression would have that many parameters in it, which would be quite a complex model to try and fit. And we'll say a bit more about that later. We wanted to do something much, much simpler. And all we want to do is model dependence between the value of a node or a trust. We tend to use the word node and trust interchangeably. You might use vertex if you're into graphs. But we want to model dependence between the value of a trust at a particular time to that trust at earlier times. Fairly simple autoregression type thing. But also to neighbors of that trust at earlier times. So if you're here and you're saying, what's going on today? Well, it basically relates to what happened at your location yesterday, but also what happened at your neighbors yesterday. And neighbors, you'll see in a second, doesn't just mean immediate neighbors. We have this concept of stages of neighbors. So let's just run through a little bit of the notation we're going to use for networks. This is pretty standard if you've worked with networks before. We've got D node, we've got trusts. We let K be the set of trust. You say two trusts or two nodes, ij, they're connected by an undirected edge, and we all denote that by I twiddles j. And the edge set is just the set of all the edges. So the set E, which has all i's that are twiddled to j. Sometimes, and we do in this case, we have a set of distances for each edge. And then the graph can be written as a set of nodes with the set of edges, or the set of nodes with the set of edges with a set of distances. What's crucial in our work is the idea of a neighborhood set. If you just let A be a subset of the nodes, just some nodes, then the neighborhood set of those nodes is basically anything directly connected to those nodes. And we can also express the neighborhood set through an adjacency matrix, S1. So S1 has entries 1 if there is an edge between, so S1 ij is equal to 1 if there is an edge between I and j, or 0 otherwise. I can hide that, can't I? There you go. So I said we're not just going to look at immediate neighbors, we also look at what we call rth stage neighbors, or sometimes some people call this rth order neighbors. And the rth stage neighbors of a particular trust or a particular node are, well, the rth stage neighbors are the neighbors of the r-1th stage neighbors. Take away any neighbors that you've seen before. So n1, it's just the neighbors, n1 of I is just the neighbors of point I. And for general R, the rth stage neighbors are neighbors of the r-1th that are not already lower stage neighbors of node I. Of course, this set could be empty. If you let R be big enough and say how many, say in this case, 7th or 8th stage neighbors are there, there aren't any, because there are no two trusts that are kind of more than 6 hops apart. Okay, so it might be an empty set. You sometimes run out of neighbors. And in fact, we use the D by D matrix, SR, as a similar thing to the adjacency matrix to encode rth stage neighbors. And I thought it'd be just nice for you to see a quick plot of the second stage neighbors, of which there are still quite a lot, and also the second and the 6th stage neighbors. There's a lot of the second stage, and there's much fewer, of course, of the 6th stage neighbors, because there aren't many kind of multi-hops to go from one end of the country to the other. So they tend to be things like, so ref is Chururo. Okay, so the only 6 stage neighbors are the ones that end up in Chururo at one end, and RNN is North Cumbria, and you'll find that most of these are up in the north, far north of England somewhere. Okay. So what do we have? We now have a multivariate time series, we have a network, and we put those two things together, and we get a network time series. We can write bold x of t for our d-dimensional vector time series, and the network time series, we use curly x, is the multivariate time series with the graph. In some problems, we have that the network can change in time. So the foot and mouth data set that we have, we're not talking about today, that network changes through time. But in this case, we're keeping to one network. We don't have it here. Sometimes additionally that you have values of some process on the edges as well, not just at the nodes. And there are models for those, one of which is developed by Mansu et al. 2023, which is called the GNAR edge model. And there are a few variants on that as well, but we're not doing that here. As we build the model now for the network time series, that's now where we're moving to. I wanted to introduce the concept of neighborhood regression for this talk. And I'm going to let ZIT of R, that's going to be the weighted combination of the rth stage neighbors of node I. So you're basically saying, if I'm at node I at time t, what's happening at my rth stage neighbors, form a linear combination of those and give that to me now at time t. All right, so this j in nr of I, that's saying what are the rth stage neighbors of I, that brings in all those values, and then you weight all those with these weights wij. So it's a kind of a regression or a weighting of the rth stage neighbors to give you this quantity z I r t. What are these mysterious weights? Well, we choose them to be inverse distance weights for the immediate neighbors. You can define what they are for the rth stage neighbors as well. I'm not going to go through that, but you can find that in the paper. Basically what this says is that if you happen to have trust I and trust J star to be close, then the value x j star t will contribute a lot to z. And conversely, if I and j star are far apart, then that xj contributes very little. So basically, if you're at trust I, you look at your rth stage neighbors, those that are far away, they contribute a little, but not a lot. If your neighbor is very close, then it's going to contribute a lot to you because they're very close to you. Okay, so standard thing. Putting that all together, we have this GNAR model for network time series. It's called a generalized network autoregressive model of order P and neighborhood order vector S, and denoted GNAR PS. And there are two components to this, or two main components. The first is something that should be very familiar. This is basically a standard autoregression of order P. Okay, so what's going on at trust I at time t depends on that trust, but in the past P time steps. Okay, with each past entry being weighted with this parameter here, alpha k. What about this bit? Well, this bit is a linear combination of the neighborhood regressions at past time points. And it does this for a set of the rth stage neighbors. And which rth stage neighbors are they? Well, it's basically if you've chosen an autoregressive parameter of P, we basically say, here you are, suppose P is 2, you take contributions from rth stage neighbors going back 1 and then 2 steps in time. But at each step back, you can choose how many spatial neighbors that you have. So if it was 1, 2, then 1 step back, you would just choose from nearest neighbors. 2 steps back, you would bring in 2 sets of neighbors, and you can choose how many sets of neighbors you get at each time step back. And that's controlled by the S vector here. So the alphas are effectively the standard autoregressive parameters. And you may wonder, I put that in quotes. That is because they're not the exact autoregressive parameters, because this model includes all the network stuff as well. So if you estimated a separate autoregression and the coefficients here, they wouldn't be the same. So if you like, they're the moral autoregressive parameters. And the beta k are what we call the neighborhood autoregressive parameters. Is how much is coming from our neighborhood in the autoregression. But hopefully what you can appreciate is that this model can get quite elaborate for larger P and larger sets of neighbors. So for example, suppose I let all these S's be 3. What that means is every time step I go back, I look at first, second, third stage neighbors. And if, I don't know, maybe you were looking at something, say weekly data, so that will be 7 days, you would have P is equal to 7 to get that weekly cycle in, for example. Well, then you'd be looking at how many models? Well, 3 times 3 times 3, 3 to the 7. Yeah, so for some of these models, you can quickly get a large number of parameters, and then doing model selection is a lot harder than for regular time series, because there's just almost like an exponential number of models you might have to look through, which can be time consuming. So this particular model comes from work in 2016 at the bottom there, and the other paper by Leeming et al. 2020. There was a very similar paper by Zhu in the Annals of Statistics in 2017, which looked at the first order immediate adjacency only. But some of you might think, oh, this looks a bit familiar, and you'd be right, because there are some models from the 1980s called space-time autoregressions, which are similar to this, but not absolutely identical, and also another paper in 2011, which has similarities with this. But why is this an interesting model? Well, one of the key things is, let's look at this parameter beta. That's the network bit. That's the kind of interesting bit, if you like. That encodes the strength of the relationship between nodes that are separated by k in time and r stage neighbors away. But the key point, the really most important thing in this whole talk probably, is that these betas are the same across the whole network. Okay? And there's a kind of way in which you might think about this. The mechanical ventilation beds data, that all comes from a virus doing its thing, unfortunately, right? And the virus doesn't care where it is. It behaves the same whether it's here or up in Scotland or wherever. So you might expect the dynamics to be roughly the same everywhere. modulo the fact that, of course, trusts aren't equally spaced on a lattice or something. You have to take account of the spacing, but then the weights take account of that part of the thing. But the point is, the fact that you've got one set of beta KRs that's concerned with a lag k in time and r stage neighbors away, and it's the same across the whole network, the number of parameters you end up with is massively smaller than you will with a VAR model. And you'll see that in some of the tables we have later on. So in some way, this model might seem wrong and too simplistic, but we take heart from the box quote, of course. All models are wrong, but some are useful. And we really use that quote a lot in this work. So that's the kind of simplest GNAR model. There are more complex variants. So for example, in this paper, we also fit what we call the local alpha model, where you can have different autoregressive parameters for each node. And more recently, not in this work, we have a local alpha beta model, which we use, which works well sometimes. The connection weights, I think I've said, but the key point about using them is you split out the effect of the parameter and the effect of the local connectivity in the network. So the W's, the omegas, the weights, they basically tell you what the local connectivity is and kind of take care of that, whereas the beta parameters are just the parameter which talks about neighbors and lag, not exactly how far away they are. So I said model selection is very important with these models, as with a lot of these kinds of autoregressions. So we have P, the usual autoregressive look back. That applies to the alphas, but also the betas here. The S's, which I've talked about, whether you're going to do a local or a global, and also the type of connection weights. I mean, here we're using inverse distances, but we've done some explorations on different ways of looking at the weights. And how does a time series person think about this? Well, probably the first thing to go to is AIC, BIC, and trying that on many models. But as I said, if you've got many models, computing that can actually be quite, there's quite a lot to do there. So we want an alternative way to do that. And the way in which we suggest to do that is using Corbit plots, which kind of give you that information to help you with model selection, but somehow also give you insight to the whole thing of what's going on. It basically gives you a picture where you can kind of absorb the entire correlation or partial autocorrelation structure in one plot and see the whole thing at once, which you don't get from maybe a whole series of AICs. Okay, I'm going to pass over to Daniel.
Just want to make sure this is working. Can you hear me? Okay, so thank you, Guy, for introducing a simple but very intuitive model, which is something nice as a statisticians, because then we can focus on what it's telling us. So as Guy said, we have a network, and that network is giving us something very useful, prior information. And this prior information, the way we estimate the model by least squares is because the network informs a very clever design matrix. But because we already have a clever design matrix, we can think of the autocorrelation structure or the second order behavior of our process and whether or not it relates to itself through the past. And intuitively, going back to the univariate world, there we have this intuition that as the further apart two points are, the less correlated they should be, i.e. autocorrelation should decrease as lag increases. In the network world, we have that, but we also have the added complexity of distance in the network. So intuitively, as the lag, which is the distance in time, increases, and or the distance in the graph R increase, this autocorrelation structure between the network as a whole object, this multivariate time series that is linked to the graph, and the network informed transformation of itself, which is just multiplying the network by the stages and the weight matrix, and the identity for the autoregressive terms should decrease. So if we go back to simple regression, we know that we can think of correlation as a dot product divided by the standard deviation of each of the variables. So here we have a dot product, and we know that we could apply Cauchy-Schwarz to upper bound this dot product, which we do. And we get this nice inequality where we can compare the magnitude of this dot product, which is some form of measuring the association between what we're interested in, which is the network h time steps ahead, and itself, and the effect of its R stage neighbors h steps behind in time. Unfortunately, if we use this denominator, we could only compare at time lag h and order distance r. But we would like to compare the HR pairs uniformly in our problem so that we can see which of these pairs have a stronger correlation, i.e. further from zero. So we do some mathematical trickery and we define this constant, which we call the autocovariance bound. And the usefulness of the autocovariance bound, which hopefully the name will become clearer once we see the plot, is that now for any choice of pair H and R, we have this nice inequality. But what's nice here is that we've encoded the network information into the lambda constant, and now we can compare a denominator that does not depend neither on lag nor on R stage. So we could compare pairs uniformly. And the key intuition here is that we're thinking of the network H steps that's ahead as a response, and of the network informed transformation, these H steps behind, as a predictor. And because we're thinking of it in this response predictor way, we can look at a scatter plot. So here we have kind of what the intuition is doing. So the white circle, this is just the 95% quantile of a standard normal multiplied by that 1 plus lambda. So it's a confidence set at the 95% level for a bivariate Gaussian using that 1 plus lambda as the variance. The ellipsoid, which is what we're interested in, is the numerator in that inequality. And what that inequality is telling us is that if there is second order structure in our network time series at the choice of lag h and our search order r, then the points should concentrate only within the ellipsoid within the sphere that corresponds to independent white noise dross. Here, the data are generated from a stationary GNAR 1.1. That is, the model is one step back in time and only nodes that have one edge between them. And we're comparing one step back in time plus the very useful neighborhood regressions guy introduced that encode this network information against the network h steps ahead. Since here we're using h equal to 1 and r equal to 1, we see this association. A very intriguing question is, okay, if the second order structure is there, we might be able to visualize it, but what happens if it's not there? So when we compare the same circle against the plot on the left, these are just white noise generated by a normal distribution, standard. And the plot on the right are the same GNAR 1.1 realization, but now we're evaluating equation 4 at h equal to 6 and r equal to 3. That is, we're looking at the association 6 steps back in time and distance in the graph equal to 3. And we see that indeed we don't have that nice ellipsoid region, and we no longer see some hint of positive association. And both of the points are still engulfed within this sphere, which is telling us that the denominator is helping us see how these points are concentrating, or whether or not that could suggest some sort of second order structure. Now, when we have a network time series realization, we want to look at many possible combinations of H and R. And for each of them, we would have to plot this, and that could be time consuming and difficult to see. So we have the network autocorrelation function as is defined in the paper, which here we don't let it vary with time, but we have mentioned this extension where we let the weights be a function of time too. And that also allows it to handle missing data, as is pointed in the Journal of Statistical Software by Guy and collaborators in 2020. And basically what we're doing is we're comparing empirically equation 4 for a given realization of the network time series, where the Hadamard product between W and SR, which all this is doing is, this is only selecting weights for nodes that are R steps apart in the graph. So in a way, we're sparsifying this W matrix. And the identity selects the components of XT, which is this autoregressive part. And then, because we have this denominator, we can compare whether or not there is some second order structure that associates this time step H steps ahead to itself after being transformed or accounting for this network prior information. We also point out that if we have a one node network and we model it as a GNAR, this function simplifies to the well-known autocorrelation function from univariate time series analysis. In that case, lambda is equal to 0, and both W and SR, well, they're they're 0. And because of that inequality, our autocovariance bound, which is in sort of a way informing how the network structure constrains the covariance structure of the network time series, guarantees that the NACF will be between -1 and 1 for any choice of HR. As Guy said, in the COVID data, there are no 7, 8, 9 R stage neighbors, which means that in that case, SR would be equal to 0, and we would only be able to compare components, autoregressive components in that case. Now, we combine this statistic with the idea of the circle plots, and we get the Corbit correlation orbit plot. And the real nicety of the Corbit plot is that just as we can look at many models for an autoregressive process in the univariate setting just by looking at the plot of the ACF, basically each lag is a model. Here, each circle represents an HR pair. So the points in the inner circle, these correspond to models that are equal to 1, that is only one stage neighbors. The points on the second circle are equals to, and then the points on the outside indicate time lag. This plot is allowing us to quickly compare 120 models. And we see this intuition behind the correlation structure. We've got decay both as the R increases at each lag, but we also got decay as the lag increases. This is for the COVID data that we're analyzing in this paper, and it suggests autoregressive behavior in this data set. So just as in the univariate setting, we are not accounting for the effects of H and R stage predictors, the best predictor is just fitting the model constrained to H -1 and R -1. And then we can just compute these residuals. And intuitively, if these residuals are recovering or reflecting the process that generated the data, they should be close to uncorrelated white noise. So their NACF should be close to 0. And that's the partial network autocorrelation function. It's just the NACF between these residuals that we've computed empirically from the data. We did not derive this using Yule-Walker-like equations. So we can extend it to any form of fitting the model. It doesn't need to be this specific form, but this is the one we use in the paper. And again, we have a Corbit plot, and it's strongly suggesting a GNAR 1-1 model. We see a very clear cutoff at the 1-1 point. So, okay, this seems interesting. Let's compare it to some other well-known models. So we compare one step ahead forecast performance 10 times. That is, we do one step prediction for 442 to 452. Realization length is 452. And interestingly, the GNAR 1-1 outperforms restricted bar, sparse bar, and AR1. And it's just the number of parameters, it's just orders of magnitude smaller, which is, it's kind of, okay, what is going on? So something we think could explain this we can think of GNAR as a var that's been shrunken at selected at the population level. So we've got our cluster vector autoregressive expression where each node is itself, p time steps behind, and the cross correlations with all other nodes. So now GNAR shrinks and selects the cross terms. How does it do this? Okay. The selection is through the R stage adjacencies. So if the R is larger than the SK at time like k, this number is equal to 0. So the gamma is going to be equal to 0, and the selection has been done. The shrinkage, coming from the definition based on distances between the nodes, only for the ones that are active, when we take that linear combination that Guy defined previously, we can also look at it as the contribution of all the nodes R steps from our node against the jth node that's also an R stage neighbor. So if this number is the largest of these ones, there won't be a lot of shrinkage. But if this number is smaller than these ones, there will be more shrinkage, which further reflects that the more we measure closeness between node J and I, the model is capturing this via the network-informed constraints. And we can write var we can write the GNR model as a constraint var, where we see that the weights are these shrunken distances. And we have this equation that connects the cross coefficients with the betas that capture the network effect and the W's that are encompassing the network structure. We also have the ring Corbit plot, which is read in the same way as the Corbit plot. This is for the PNACF, for the COVID data, and we're looking at the partial network autocorrelation for the 3 waves of the pandemic. So the first wave was from April 2020 to July 2020. Then we've got the gap from July 2020 to September 2020, and the second wave from September 2020 to July 2020. And we see that the plot suggests that the partial network autocorrelation was strongest during the second wave. Yeah. And then I'll go back to that. Right. Oh, really? Okay. Oh. Tiempo.
Okay. I'll try and wrap up. So I'll go a little bit fast. So we fixed on a GNAR 1.1 model, as Daniel says, and that's the model there, the whole model for all these data points. So 0.95 of what happened before, plus 0.043 of what happened before at the neighbors. And you may say, well, it seems like a standard autoregression. That 0.95 is about 20 times larger than the network effect. But then the trust I typically has many neighbors, so the network effect can be substantial because that gets aggregated up. So I'll have to go through this a bit quickly. You can look at the details in the paper. We have a concept called node relevance, which we call glob index. Here's a plot of the glob index. So this somehow measures relevance of a particular node's contribution to the overall autocorrelation. And you can see here the purple colors are kind of least relevant. The yellow is the most relevant. And you can see it's most relevant in kind of the London area and the Northwest. That's a bit confused, that plot. If you wanted to look at the top 10 trusts according to the most relevant, then you start at Buckinghamshire, and then the top, the 10th one is Oxford University Hospitals. But we can plot these. So we're going to plot the top 11 urban centers as blue dots. Black squares are the 10 least relevant, and the red dots are the top 10 most relevant. And if you look at that plot, so the blue is actually just population centres in the UK. That's why this Scottish region is here. And that's why we chose 11, because we wanted 10 in England. So that's the others. The least relevant are these guys here, and then the most relevant here. So you can see there's most relevant to the northwest of London and the northwest of England there. And that's 60. You can look at the papers, but you can see the clusters don't change much. Going from there to there, it's still the same, that they're just in that area. So the 2 main clusters that I talked about, none of the top 10 globally relevant, glob index relevant trusts are in urban centres, which we thought was interesting, but they seem to be intermediate. But it's still curious that there aren't highly relevant trusts to the south and east of Birmingham, between Yorkshire and Tyneside, nor to the south and east of London. And we asked the question, can any of this help with mitigations? The lowest glob index appear to be at the extremities of the network, nearly all near the coast, and perhaps not surprising because you can't further the virus on the edge of the network into the sea. Why do GNAR models forecast so well? Well, we think the secret is they have very few parameters relative to vast amounts of data. So the GNAR 1.1 only has 2 parameters, and if you've got the 63,000 data points, then you've got 30,000 data points per parameter. Contrast that to the simplest var1, which has 19,600 parameters. That'll only be 3 data points per parameter. So there's a big difference there. So GNAR might well be completely the wrong model, but whatever the wrongness is, it's being estimated extremely well. Model selection we've talked about, so I won't go over that any more detail. Just finally, what next? So we're working on versions of these models that look at different communities. So you could, for example, here look at non-urban and urban situations and then have different parameter sets on those and then look at interactions between those. We're looking at cases where you have more than one network time series, so multiplex networks. So as I mentioned earlier, the foot and mouth data set where you could have kind of like physical transmission and wind-borne transmission. You could look at examples where you have vectors or matrices at each node, not just a univariate time series. That could be where you have more than one measurement at each trust, not just this statistic, but other things as well. And then we're doing a lot of work on other methods of forecasting and network construction. Can you use the forecasts to improve what kind of networks that you've got? So we've been doing some work on CPI inflation on that. So last slide. The code and data is available in the GNAR package, which you can get on CRAN. There's also a Python version that you can get hold of now. And I just wanted to, I had to finish off somehow, so I nicked this quote from the COVID inquiry. Don't read it all, but the last thing I think really chimes with what we're trying to do here in this work, and it says statistical modeling of complex health services data has an important role to play in this crucial initiative. So that's what we're all about. So thank you very much for listening, and that's the end.
Daniel. Now we're moving to the proposer of the vote of thanks, and I would like to call on Sarah Heaps from Durham University.
Thank you very much to Guy, Daniel, and Mario for such a wonderful talk. And thank you also to the organisers, in particular to Ben, to Judith, and to Ruth for inviting me to be a discussant. It's an honour. Okay, so I guess I don't really need to give much of an overview of the paper, given that we've just heard a very nice overview. But I guess just to point out a couple of the things that I think are the kind of the most important contributions of the paper. So the first is, of course, the new association measures, which we've just heard all about. So the network autocorrelation function and the partial network autocorrelation function and the associated visualization tools, the Corbit plot and the Corbit plot. And the other thing, which we haven't heard as much about, is the new theory that the authors developed, which really sheds some light on the properties of the GNAR process, which I think is really nice. So the first thing that hasn't really been mentioned is this really nice link to graphical modeling through the R stage neighborhood structure by essentially a representation through the spectral view of time series analysis. And this is really nice because essentially it says that the kind of 1-stage neighbors are the most important, then the 2-stage neighbors are the next most important, then the 3-stage neighbors, and so on. And eventually, when we get to a point at which the 2 nodes in a network are separated by enough edges, and that separation, that threshold depends on the maximum R-stage depth, they become conditionally independent given all of the other nodes. Okay. And then there's also this nice interpretation, which Daniel talked a little bit about, as of a sort of GNAR process as a constrained vector autoregression with these nice properties of variable selection and shrinkage, which are determined by essentially strong prior information. And that came in the form of, specification of the network and its associated network weights. Okay. So I guess at this point, I'm kind of going to focus on some of the things that I found the most interesting about the paper, which are in some ways complementary to the things that we've already heard. So kind of the things that I thought were really interesting was this new theory that was developed in the context of the GNAR processes. Okay, so I guess my background is in multivariate time series analysis and Bayesian inference for multivariate time series analysis. So this is kind of where I'm coming from. But I really liked the new theory that the authors developed because it really helped me to see the place of the GNAR process in a kind of growing body of literature that's developing at the moment. So essentially, vector autoregressions are by far the most widely used tool for multivariate time series analysis. But the problem with them, as has been highlighted, is that the number of parameters grows quadratically with the dimension of the observation vector. And so in order to make inference scalable, people can do things like they can allow sparsity in the autoregressive coefficient matrices and so on, but there's still a huge number of parameters to estimate. And so what people are doing increasingly now is they're actually imposing structural constraints on the vector autoregressive processes to facilitate model fitting and also to facilitate I guess, a reasonable reduction in epistemic uncertainty. And so there are a number of ways of doing this. Well, we've seen one already, that's the GNAR process. Another kind of class of models that do this are dynamic factor models. So the idea here is that instead of having an observation vector being modeled according to a vector autoregression, instead we have some much lower dimensional vector of latent factors that it evolves according to a vector autoregression. And then we treat the observations as being some kind of noisy linear transformation of those latent factors. Okay. And I guess some work in this area, which sort of relates to what we've heard about today in the sense of its use of prior information, is some work that I did with a colleague, Ian Jamin at Durham University. And so in our work, we were focusing specifically on the class of stationary dynamic factor models where the stationary variance matrix was meaningful. And we were taking a Bayesian approach to inference. And what we did was we showed how through the prior distribution for the factor loadings matrix, we could encode ideas about the stationary variance matrix. So in the COVID-19 application, for instance, we would encode the idea that the trusts that are closer together would be more highly correlated than the trusts that are further apart. I guess another way, another kind of broad class of models which tries to reduce the dimension of a vector autoregression usually deals with the specific case of graphical vector autoregressions. So this is where we allow zeros in the autoregressive coefficient matrices, which then endows a graphical interpretation because these zeros have a meaning in terms of Granger non-causality. And what people will do is they'll essentially, within these graphical vector autoregressions, they'll impose constraints on the autoregressive coefficient matrices. So a popular way of doing this, for example, is by taking the autoregressive coefficient matrices at the different lags and to arrange them into a three-way tensor and then to employ some kind of tensor decomposition method. But the thing that all of these ideas have in common, and they have in common with the GNAR process, is that they retain interpretability. So as I mentioned in the GNAR process, we have this nice idea that if nodes are further enough apart on the network, they become conditionally independent given the other nodes. We have similar concepts and similar interpretable ideas coming into play with these classes of models. So for example, in dynamic factor models or any other model which uses lower dimensional latent structure to build up the time dependence, what we find is that we can quite often, bestow the latent factors or whatever they are with some kind of interpretation, which helps us to understand that, the big and complicated data set. Similarly, in the context of the graphical vector autoregressions, they have this kind of associated mixed graph, and things like Granger causal Markov properties, which have been worked on a lot by, for example, Michael Eichler, allow us to essentially relate separation properties on the graph to statements of Granger non-causality. Okay, and so I think my point with this slide is that I think these GNAR processes and the extra theory that's been developed in this paper is really part of a growing body of literature on reducing the dimension of vector autoregressions to make them more scalable, but doing so in a way that allows the models to continue to be interpretable. Okay. Oh, I don't know what happened there. I know you're getting a sneak preview. Okay. So possible extensions. I guess my idea is that, well, there are obviously some network time series where the network really is observable. So this might be, for instance, if we have a social network and we really do observe the follower-followee relationships. But there are, of course, lots of other networks like the COVID-19 application in this paper where the network wasn't observable, okay? And so I guess my idea is that, well, what about we try to learn the network and the associated network weights? And if we were to do this, then a very natural approach to inference, in my view, would be the Bayesian approach, because all of that lovely prior information that could be used and that was used to, design and construct the network and to construct the associated weights could be used to center a prior in some way for the network, for example, through a mode, and to center the prior for the network weights. If we were taking a Bayesian approach to inference, we could also incorporate cumulative shrinkage process priors, essentially for the autoregressive coefficients at increasing lag, to increasingly shrink them to zero as the lag increases. And similarly for the autoregressive coefficients in neighborhood R stage sets, to increasingly shrink towards zero as the R stage depth increases. And one of the nice side effects, if you like, of these priors is that typically it will allow you to identify, in this case, the lag, and also it would allow you to identify the number of R stage neighbors you needed for each lag. If we were to take this Bayesian approach to inference, I guess questions that you would want to ask would be, well, how can we use the network autocorrelation function and partial network autocorrelation function to choose upper limits for the H lag and the R stage depth? Because these would be ingredients that we would need to be able to make use of these cumulative shrinkage process priors. And also, how can we develop efficient algorithms to update the R stage adjacency matrices when we make minor modifications to the underlying network? So just to end on some questions for the authors. So I guess my first question is kind of about the data. So we've already seen a version of this plot. So if you look at the plot on the top left, this is the log transformed data. It's 140 blue lines, each of which corresponds to an NHS trust. And then there's a red line which corresponds to the mean. And essentially, when I look at that plot, that isn't really consistent with a stationary vector autoregressive process of order 1, because the regression to the mean is just far too slow. And actually, if we go ahead and we divide the data up into the 3 segments, because the authors did identify different correlation structure in the first wave, which would be over here in the gap, and then in the second wave using the nice Corbit plots. But actually, within those segments, we still don't have data that look like they arose from a stationary autoregressive process of order 1. And actually, if we look at the estimates of the of the coefficients, we have 0.95 for the typical autoregressive effect, sometimes called the momentum effect. And we have an estimate of roughly 0.04 for the neighborhood effect. And in the paper, the authors actually provide a nice sufficient condition for stationarity. And that condition is that the sum of the absolute values of those terms has to be less than 1. And it is, but only just. So we're really on the boundary of the stationary region here. If, on the other hand, we look at a time series plot of the first differences, that's the plot on the top right. So this is much more consistent with a stationary autoregressive process of order 1. And in actual fact, if we look at the estimates of the parameters down here, we're now kind of comfortably within the stationary region. So if I look, well, I was interested to see in the paper in Appendix A1, the authors did actually report the results of model comparison in which they used the difference data. So they compared the GNAR process to several competitors, the same ones that we saw before. And now we find that the kind of predicted performance of the GNAR is comparable with that of the sparse vector autoregression and the autoregressive process of order 1, whereas previously the GNAR kind of outperformed the others. So I guess my question to the authors is, did they explore any further? And in similar situations when the data don't really look like they arose from a stationary vector autoregressive process, would they recommend taking differences? And if not, sort of why not, I guess? And finally, just some more general questions, which very much are kind of motivated by things that I've said. I guess when I use a PACF, for example, to identify the point at which the partial autocorrelations cut off to 0, if I'm trying to identify the order of an autoregressive process, I very much rely on the significance intervals, okay? So I guess I'm wondering whether there's any kind of associated measure of uncertainty that can be associated with the network ACF and the partial network ACF to help in the interpretation of the Corbit plots. And I think this is particularly relevant because, as we've seen in the Corbit plots, the magnitude of the function values are only presented on a relative scale, so using color or using size, okay? And again, my second question, I guess, related to this idea about perhaps trying to learn the network, I was just wondering, in a kind of hypothetical scenario in which the data really did arise from a GNAR process, what would be the effect on the network autocorrelation function or the partial network autocorrelation function of misspecifying either the network or its weights? And finally, as I mentioned, the authors provide this really nice sufficient condition for stationarity in the paper, but I was wondering whether it might be possible to identify a necessary and sufficient condition, because if we wanted to constrain inference in a Bayesian context to the stationary region, we want to be working with the whole space. And that's it.
I'd like now to call on Anastasia Mansiu from Warwick University to second the vote of thanks.
Thank you very much to the organizers for the invitation, for being the seconder of the vote of thanks today. Before I start, I have to say that I really enjoyed reading this paper, and congratulations to the authors for the very nice contributions in the literature. I will start with a short summary of the paper, just emphasizing some key aspects of the paper. So first of all, the authors introduced new tool for model selection for network time series. And notably, they use the network autocorrelation function, as it was very nicely presented by the authors and Sarah as well, and the partial network autocorrelation function. They also introduced graphical tools to be able to visualize these measures in order to allow model selection with respect to the lags and stages of neighbors. And also, there is a very important new theory that the authors developed with respect to the association between the GNAR model and the graphical models for time series, as well as to VAR models. The key contributions from my point of view and the other researcher who has worked with this class of models, I believe that the major contribution is the fact that the authors tackled the challenge of model selection for network time series by developing measures that explicitly account for the network structure. And this is very important for practitioners. And also, another contribution is that they provide a very convenient visual representation in order to determine the lags and stages of neighbors. Also, the relations that they identify with respect to between actually VAR models and GNAR models allows further interpretation with respect to the node relevance on the correlation structure, which also reveal very interesting results, as we saw earlier from the presentation of underlying clusters, ultimately clusters of nodes in the network. So my first comment is related to the network structure uncertainty, which is something that also Sarah introduced, brought into on the table. So a limitation of this class of models is the assumption that the network is precisely observed. However, networks are complex objects and they're highly prone to measurement error. And due to this network uncertainty, if you do not account for this could have potentially an effect on inferences and then respectively on the model selection process that the authors propose using the metrics that they propose. And in my point of view, like looking into the future, it would be interesting to account for this network uncertainty because currently the literature lacks in methods for accounting for it. So in the following two slides, I have two possible directions to propose, but apparently there might be many more ideas. So I'm very happy to be part of this meeting today and discuss about this. A possible direction would be to consider the measurement error models literature on networks. So the key assumption in this literature is that the observed adjacency matrix, using the notation by the authors denoted here by S1, is a noisy version of some true, non-observed adjacency matrix S1 true denoted here. So there is this interesting study by Lee and Lee, which was published in 2022 in Series B, and they introduced a linear regression model for noisy network link data. This is not for time series, network time series, but still I believe that this could be a study that we consider for further extension to network time series possibly. And ultimately, they introduced this linear regression with a network effect, that the network effect lies in this space, which I denote here by PKS true, which is the subspace spanned by the k leading eigenvectors of this latent adjacency matrix S true. So the intuition for this is that the spectral space ultimately captures both microscale and macroscale properties of the network, and it's more robust to perturbations, to local perturbations of the network, and that is why they're using this subspace here, the spectral space. And one approximation that one can use, and what the authors propose, is ultimately use this observed adjacency matrix S1 as an approximation for the true non-observed adjacency matrix, assuming that this is a perturbed version of the true matrix. But also the authors, in case you don't have this prior knowledge, like observed adjacency matrix, they also propose network models in order to approximate the non-observed adjacency matrix. And they propose for inferences a spectral projection estimation. An alternative way for capturing the network uncertainty is actually borrowing similar ideas to what Sarah mentioned. So developing a fully Bayesian framework and then assigning a prior on the network structure, still assuming that there is this latent network as true, which we can treat it as a latent parameter. And actually, the advantage of using this approach is that you can also assume a similar noisy version of the weights of the network, of the edges of the network, with this W true matrix. And then you can use this information of the observed adjacency matrix in your prior. But potentially also what would be interesting is to consider possibly multiple realizations of the adjacency matrix that can be considered as noisy realizations of the true non-observed matrix. And this is again relevant to the COVID-19 application, where, as the authors also mentioned, there is more than one way to construct a network. And then inferences can be made using, for example, an MCMC and specifically a Metropolis Hastings step for making inferences on the network structure. Similarly for W true. And potentially also the advantage of the Bayesian framework is that you can also account for the uncertainty with respect to the lags and stages of neighbors. Actually, Sarah had a very nice proposal here, because I guess my proposal is a bit tricky with a reversible jump. It can be definitely more challenging in combination with inferring a network structure. So also I have a more general comment and slash question to the authors, and this is with respect to extensions to other network time series models. For example, recently there is a work that accounts for node heterogeneity, and I was wondering about the effect of underlying clusters of nodes in the association between the time series, and if we if we have prior knowledge about these clusters, whether this can be incorporated in these measures to account for it. And then some further general comments and questions only on the COVID-19 application. Actually, some of them have already somehow been answered by the authors by the nice presentation. The first one is with respect to the transformation. So I would be curious to see like further statistics on the row time series. Actually, the authors did provide today some graphical, like we could see the count time series actually, which is information that I didn't have earlier. And then as also the authors acknowledge, they could have implemented a Poisson network autoregressive model. So these are network autoregressive models for count time series. And so I would be also interested in seeing comparisons with the PNAR model, which was developed by Armilotta and Fokia-Noss. However, I think also that given the indication from the exploration of the authors with respect to the node relevance index, where this indicated the presence of underlying clusters, I would also be interested in seeing whether a PNAR model with a block structure, we have actually a paper with my co-authors Reinert and Hang, whether this would potentially have a better prediction performance or not. And finally, the inclusion of different adjacency matrices. So this is another question, whether this would be meaningful to be incorporated in the part of the model selection, like through the Corbit plot, potentially through the R Corbit plot. And then finally, just a minor comment. I really find very, very convenient this way of visualizing. It's very convenient actually for the practitioner to determine the lags and stages of neighbors, especially because of the different colors used for indicating the size of the measure of the partial network autocorrelation function. So as a new lecturer who actually taught a data visualization module, my only comment here is that it's hard to accurately assess by area. So the size of the points are indicating ultimately the absolute value of the measures. So potentially using alternative ways, either discretizing the scale or, given that it's negative or positive, still having by shape potentially being changing from negative to positive. But this is just a minor comment. And this final comment on zero stage neighbors actually relates mostly to the previous slide. So I would also be interested in the COVID-19 application to see whether a simpler model without a network structure, what is the performance and what if potentially it has better prediction or not. Yeah, I will conclude here, and here are some references.
So we would like to thank our presenters today for their excellent and insightful talks. As per tradition, let's mark our appreciation by applauding. So now we will move on to the open discussion. We'd like to encourage you to comment or raise a question on the paper, and it can be brief or up to 5 minutes long. If you're here at Imperial College, please raise your hand and come up to the lectern when called. If you're online, use your raise hand icon or put your request to speak in the chat. All comments can be written up afterwards and submitted for publication with the paper in the journal. So we're going to start now with those who have given their names already. And I would like to call Konstantinos Fokianos from the University of Cyprus and Mirko Arbiliota from Tor Vergata University of Rome, and they are online.
I will talk first for like 2-3 minutes, and then Mirko will integrate the presentation. So many thanks to the authors for this interesting paper, and it is a very nice, stimulating paper, and I'm happy, to hear all these comments from the previous discussions. So just to recap, we have a network of n nodes, and there's an adjacent matrix which just consists of 0 and 1s. So the one is whether we have two nodes that they are close together and 0 otherwise, and we can have also undirected graphs. So this matrix, the adjacency matrix, is non-random, and it is known, and it's reasonable for many applications, as the author said, because we have cases like, for example, we have geographical distances that can determine the neighbor and so on. So, or we have borders between counties, so this can give us information about the neighborhood structure. So YT is a high dimensional time series. You observe a time series at different nodes, and then you have a multivariate time series in the network structure. And this is exactly what the authors try to model, and they do it very nicely. And we want to assess the network effect on YT over time. So as it was mentioned, to model YT by a vector autoregressive model, sometimes people, of course, are doing these kind of things with sparsity and factor models, but it requires that we have the number of parameters grow exponentially, like n square, and this is usually very, very larger than t. So the network autoregression is doing exactly this. It reduces the number of parameters, so we can see it as also a dimension reduction method. So we take the ith node at time t, and we regress it on the past neighbors at time t minus 1, and the value of the node at time t minus 1. So there is a nice interpretation because of linearity. We have a network effect. This is the beta 1 in this equation, is the average impact of node psi connection, and beta 2 is the autoregressive impact. So the authors contribute to network autocorrelation function and Corbit plots, the partial autocorrelation function, connections to graphical models, and also they talk about selection in regex. My first comment is, it was already mentioned, that there is a close connection of network time series to space-time ARMA models. And actually, it is nice to compare the approach taken by the authors, especially in terms of autocorrelation and partial autocorrelation function, and also to compare with other traditional measures of spatial correlation. So this formula gives the cross correlation between the weighted Lth ordered neighborhood and the kth ordered neighborhood at h time lag apart. So it's kind of interesting, to actually compare the approach taken by the authors. And this formula is estimated exactly by the empirical counterpart, and we can definitely similarly define the autocorrelation function based on the second formula you see on the display. and the corresponding estimator, of course. And now for the special case of autoregressive models, there are Euler type of equations that yield the partial autocorrelation function. I think these points should be addressed somehow and compared. Maybe Mirko now can go over, and I will just scroll the slides.
Thank you. I hope you can hear me. So I would like first to also express my gratitude for being part of the discussion and congratulate with the authors for the really nice and interesting contribution to this stream of literature. So I would like to just point out a bit more the problem of the modeling of count time series data. I've seen that, of course, this came out several times, couple of times during the discussion. So here I would like just to point out a few details on when we try to model count time series. So the example of the COVID data is a classical example in which we have counts. So in the contribution, the authors have log transformed the data, of course, to obtain continuous value data that can be used in an autoregressive-like network, autoregressive-like framework. Of course, as it has been mentioned, there are models for specifically suited for count data, and we introduced in particular the Poisson network autoregressive model that is here restricted only to the first stage neighbor, but can also be extended to higher order neighbors. So I would like to point out here a bit the structure of this model that resembles the same structure of the GNAR model we have seen so far. The only difference, the relevant difference, is that the data are conditionally to the past Poisson, depending on a dynamic Poisson mean lambda, and this is modeled in a GLM style as a purely depending on the past data with a network autoregressive structure. And it is important to use this model, I think, especially for COVID data, because in the sense of comparison with other models and forecasting, with this kind of models, we are sure that we can forecast counts, basically. We can forecast a non-negative conditional means of the counts. By using transformation, we can obtain results, for example, negative forecast, and for COVID patient bed, of course, can be not immediate to be interpreted. And we avoid the arbitrary choice of log transformation or other kind of transformation to make the data continuous. Moreover, in general, we have also introduced a non-linear version of the models for count and continuous data. So it would be nice to see the application of these models with a non-linear framework, and also to analyze a bit how to interpret the network ACF and PACF introduced by the author in the case of non-linear framework. So these are some examples of nonlinear models that can be used for modeling the data. The most famous probably are the threshold model and the smooth transition version of this model that are again included into a network autoregressive-like framework. So this can be, I think, an important part of further discussion in this literature. And of course, we have also a package called the PNAR that does some of the interpretation of these nonlinear models in NAR. So to ease the comparison can be a good idea. And plus also some extra comments about the interpretation as an oracle solution of the GNAR model. This is nice, actually. I was wondering, in the case in which you have a network that is not sparse, like inverse geographical distance, then what happened to this interpretation in terms of sparse network that is an oracle solution of a shrinkage problem? And also especially important for COVID data, what happens if the data are non-stationary? We see that there are high peak and a period of relatively calm situation. what happens if the data are not stationary or if there are unit root to the network ACF and PACF, and maybe how to tackle this problem in future research may be of interest. That's all. Thanks for the attention, and here there are just some references.
Thank you very much. We would like now.
Thank you.
We would like now to call David Hand from Imperial College London, who is in the room.
So before I come onto the paper itself, I should remark that I am possibly unique in this room, not an expert on time series analysis. So when I opened the paper on Sunday afternoon, I had no great expectation of understanding it, let alone making a contribution to the discussion. But I'd like to commend the authors because, as it turned out, the paper was exceptionally clearly written, and I certainly felt that I understood it. Indeed, I now feel that at a pinch, I could actually probably build a GNAR model myself. However, although you knew there was a however coming, and although I found the description of the GNAR model itself exciting, I felt rather let down by the example. It seemed to obscure rather than reveal the power of such models, so that I found myself asking what was the real objective of the paper. Clearly, the model and the associated graphical tools described in the paper provide valuable instruments for condensing the data down to a comprehensible form. The paper says things like make sense of high-dimensional dynamic phenomena, interpretation and inference of relationships present in dynamic phenomena, and interpretation of the relationship between those. But it wasn't clear to me how this would facilitate the preparedness, resilience, and response referred to in the conclusion when discussing the motivation between choosing the COVID-19 pandemic example. To do those three things, surely one needs A, some understanding of causal relationships, and B, predictive power. Now, as to the first of those, the word causal is conspicuous by its absence from the paper. And as to the second, I note that lurking in table 2 is the naive model of, I think, essentially last value carried forward. And it turns out that that predicts almost as well as the GNAR model, at least in terms of the mean squared prediction error for one-step prediction. Judging from that, a more useful predictive model would be one which identified those nodes where last value carried forward didn't give good predictions and focused on those. So this is not a critical comment on the overall merits of the paper, which I think provide a lucid description of a type of model which will be of immense value in a wide number of applications. Certainly, I can think of other areas that I've worked in where I would love to apply these sorts of models. Rather, it is a criticism of the choice of the example, which I think fails to demonstrate the power and applicability of the model type. Thank you.
Thank you, David. So now I would like to invite contributions from the floor. So please raise your hand and give your name and affiliation. We need to note your details so we can follow up with you later for the written version of your contribution. And it will be published in the journal alongside with, yeah. Okay. So would you like, do they have slides? So would you like to share your camera, Andre?
Hi. Do you hear me?
We can, yes.
Thank you. Thank you for allowing to discuss. So I will be rather brief. Thank you for the paper. I'm also not directly from the time series literature, but the paper I think brings very interesting topics also in terms of network analysis, which are a very frequent topic in general and in recent years in probability theory. So I think that it opens up also a question of a shape or type or properties of the network or graph that random graph, if you wish, that is discussed. So the question is, could this network model that you have be analyzed also differently if the network would have any different properties in terms of if you would consider it as a random graph? So even one possibility that was discussed also in the discussion meetings in recent year was network archaeology in terms of the COVID-19 properties. We know, like it was mentioned by I think Anastasia Mansiu, that you had many different possibilities of modeling these networks. They were modeling by stochastic processes like Sayre, like compartmental modeling, and so on. So in terms of the random graph possibilities, could networks also be included in a different manner? And then how basically to study it, and could it not tell more about such properties? Naturally, also time series are highly frequent object in different probabilistic aspects. Thanks.
Thank you very much, Andre. Are there any contributors from the floor? Yes.
Hi, Stephen Gilmore, King's College London. So like the previous two contributors, I'm far from being an expert in time series analysis. I was going to congratulate the authors that they know, when you know you've written a very clear and accessible paper, when somebody who knows nothing about the topic stands up to contribute to the discussion. So I just have one question really, which is about the data. So Guy mentioned that the virus doesn't care where it is, it behaves the same, irrespective of where it's starting from. And likewise, the virus doesn't know that there are 4 nations in the United Kingdom. So my question was just, isn't there some adjustment needed for North Cumbria? Carlisle's not that far from population centres in Scotland. Bristol, for example, is not that far from population centres in South Wales. And I wondered, is there any way, I couldn't think of an obvious way within the author's framework to adjust for that, but I wondered if they had any suggestions about how that might be done. Thank you very much.
Hello, everybody. So I'm Christian from the University of York. So I'm going to read quite quickly the contributions that we sent to the journal. So first of all, we would like to congratulate the authors on their insightful paper and valuable contribution to the analysis of network time series by developing new tools for studying such stochastic process. At the heart of this development sits the generalized network autoregressive GNAR model that originally proposed by Knight all in 2020 and extended to, for example, incorporate covariates, also model edge-based time series, and forecast. Through this work, Nation 25 all introduced novel time domain tools, namely the network and partial network autocorrelation function, and associated Corbit correlation orbit visualization plots by the authors built also graphical models for time series by theoretically connecting the GNAR formulation to a latent graphical process. Their theorem 2 identifies 2 important structural properties. First, the connection to partial correlation graph generalizes earlier edge-based notions of dependence in Dalhouse sense, where dependence is now captured via active R-stage neighborhoods instead of direct connections. Second, the assignment of R-stage GNAR adjacency is connected to a cross-spectral hierarchy under the intuition that nodal dependence is the strongest between the first stage neighbors and it weakens as R increases. Regarding the first point, a key implication is that zeros in the inverse spectral matrix no longer imply a direct node pair disconnection, but rather the absence of a path of length at most to R between them. So where R denotes the largest active R stage neighborhood regression of a particular GNAR model. With increase of an active neighborhood regression, the GNAR induced adjacency becomes denser, thus potentially reducing interpretability in the dollhouse sense. When R exceeds the network diameter, the structural advantages of GNAR over VAR models may no longer be exploited via the GNCC sparsity. These observations raise a crucial questions. Can we still recover interpretable network structure from the data when the sparsity and the estimated inverse spectrum no longer directly maps to edge absence? In the second part of Theorem 2, Nason et al. 2025 established the existence of a cross-spectral hierarchy connected to active neighborhood regression. The authors define our stage-dependent inverse GNAR spectrum using a complex substressful operator underpinned by the property that the strength of nodal dependence decays with increasing R. Whilst insightful, this approach relies heavily on set of threshold levels, hence raising questions about their practical estimation and interpretation. Finally, connecting these 2 points, the R-dependent inverse GNAR spectrum gives rise to an R-stage partial correlation graph. Notably, once a pair of nodes becomes conditionally independent, the subthreshold operator maps the corresponding entry to 0 for larger thresholds, allowing the Latin graph to be pruned based on conditional cross-spectrum strength. This structure links the edge in the underlying network to the intersection of R-dependent S-sets and the active nodes FPR. Could the hierarchical structure that you defined in the second part of Theorem 2 provide a pathway for inferring underlying network structures when the network is unknown? Thank you very much.
Are there any other contributions from the floor? Yes.
Hi, I'm Zaid Askar from University of Lincoln, and I really appreciate your talk today on an excellent paper. I would just like to just kind of take away from this because you mentioned that all models are wrong and they have some really good predictive powers. And here, I would say is that there are models which exist in infectious diseases and other the deterministic models, the stochastic models, and other graph models. And where would your theory would really be beneficial is if you can actually predict the transmissibility parameters, the betas, and as you say, the COVID once it spreads, the betas are going to be the same everywhere. And I think if you could somehow incorporate the other contact patterns or the the network patterns, that's the social network pattern within that would be really beneficial. I think. Thank you.
Thank you very much. Any further contributions? So in that case, I'm going to ask the honorary secretary to read the following written contribution from Nuo Shu and Fengkang Zhu from Jilin University, Changchun, China.
So good afternoon, everyone. I'm Ben Swallow, honorary secretary and editor of the discussion papers. We've received 2 written contributions, very helpful questions. Just read one of those, so that saves me a job. But we also received this contribution from 2 authors as well, as Rich just mentioned. Just because there's quite a lot of mathematical notation, it helps. They're very hard to try and read some of this out. We congratulate the authors for introducing thought-provoking and meaningful new tools for network time series modeling, network autocorrelation function, and partial network autocorrelation function. The corresponding Corbit plot provides reference to model order determination and interpretation. As noted, the set of estimated autocorrelation coefficients at different lags tends to be independently and normally distributed with mean 0 and variance of order 1/t. It is generally accepted that autocorrelation function values falling within an interval plus and minus 1.96 divided by the square root of t can be approximated as 0. We are particularly interested in whether similar conclusions hold for the NACF. This is also critical for adding reference lines to the Corbit plot, allowing us to directly evaluate the selection of the model's lag order H and R sleeve neighbors. We primarily focus on the definition of ANCF as shown in definition 3, This depends not only on the time lag h, but also on the R stage naders, and the influences of these two components are comparable. Inspired by this, we discuss a more general definition of NACF, as shown in the contribution, where eta is the weight of the balances, the heterogeneity and autocorrelation between temporal and spatial structures, and the lambda, which is different from the one in definition 3 presented in the paper. The matrix, as shown here, enables us to calculate the prevalent changes across the entire network by considering the linear paths assigned to each node, where these paths are subject to distinct influences from both temporal and spatial dimensions. If we define y as the mean-centered time series and wi to be the height row of the matrix W, then the authors propose this alternative inequality. And by similar arguments to proposition 3 in the supplementary material, an additional inequality as shown here, then again, the NACF is bounded between -1 and 1. They show that, or can be shown that when eta is a half, the NACF is equivalent to equation 9 in paper. And for a trivial GNAR model with a single node network reduces to the ordinary autocorrelation, then we consider the minimizing the LP norm of the covariance matrix sigma. Then we consider to select the optimal eta for a fixed path. Otherwise, if we let the NACF be the column-wise components, we obtain a maximum likelihood eta hat for fixed h, and besides, we can also consider other criteria such as minimizing the determinant or the trace of the covariance matrix according to the specific situation. So thank you to the authors for their contribution.
So as we reach the end of the discussion meeting, we now give the opportunity to the authors and co-authors to reply. You have 10 minutes.
Thanks. Do you want to stop sharing? Thank you very much. We'd like to thank especially the proposer and seconder. I had the unfortunate task of having to read through the paper, but thank you very much for your contributions. They're most welcome, as are all the discussion contributions that came in today and before. So thank you for that. I mean, we've got pages of stuff written down. And I know I've only got a short time, so we'll focus, if I may, on some of the maybe key points that were maybe mentioned by more than one discussant. Kind of what's underlying a lot of the GNAR stuff is that we just sort of had frustration with VAR models trying to fit things when you had vast numbers of parameters, you didn't have enough data, and you somehow think, but we know some more about these time series. We know stuff. We've got, we know how these are connected. Or these two sites are so close together, they must be somehow, not necessarily talking to each other, but associated. And so that's what motivated the GNAR. But as certainly both the proposer and the seconder say, there's a lot of mileage to be had to be thinking about the network some more. Certainly a lot more than we did. And, we mentioned going off down the route of time-changing networks, and that's an exciting area. But actually, probably more important, as they've said, is that you've got to do something more about the network uncertainty, misspecification, perturbation methods, I think, were mentioned, and, accounting for uncertainty in the network. Because you can see the network we got here is essentially kind of made up based on some intuition. Kind of aligned to that was, well, why not build in some more Bayesian methods? That's definitely a good idea, certainly on the network. We are groups of people, us and some others, are working on maybe more traditional, attaching Bayesian methods more to the parameters, and thinking about Richardson Green algorithm, which is kind of thing that you'd want to look at there. So thank you very much for that. On the first differences on the time series, so yes, you're right. when you do the first differencing, you look at those forecasting errors, then they're not that dissimilar to some of our best ones for the undifferenced data, but actually still the undifferenced data is still the best by a bit, and that's why we kept it in. But since we did it with a difference and we thought it was pretty close, we thought, to be honest, we ought to put that in the supplementary. At least people could see that. But I think what's interesting about that is when you do look at the differences, it becomes clear that probably what you've got there is a fairly constant mean in the differences, 0, but you've got a real time changing variance, and they do align with the different waves, which is not that surprising. So thank you for drawing attention to that. And there are people working on time varying versions of that with the second order non-stationarity. So thank you very much. So I think at least two discussants mentioned the idea about how do you assess the size of the covariances. You know, in the normal time series, you have the plus or minus root 2 over n, 2 over root n or something. Be nice to have something at least for that here. Yes, completely agree. Definitely something we should look at. Of course, if you do it in a Bayesian way, it probably comes out better anyway. So yeah, that's something that needs to be looked into. And in fact, we were really surprised that nobody said, "Where's your forecast intervals? Why are you forecast?" You know, and so we'll say that now. Block structure was mentioned by the seconders. Thank you very much for that. I think there are some papers on GNAR with communities. It isn't quite the same thing, but it's kind of going in that direction. So that's going to be interesting. I mean, this whole area is exploding. I mean, we were talking earlier that we submitted this paper, I think 18 months ago, but we were working on it before then. But since then, kind of the whole field has just moved on rapidly. It's a very fast moving area. There was also a comment about different adjacency matrices, which I think is very, very interesting. And there's a very interesting data set, COVID again, which is New York COVID cases. And there you can actually have different networks based on a covariate. So you get the idea of like network factor models, where the factor is actually a network, not a variable, which is quite interesting. Thank you very much to Armalotta and Fokianis, a brilliant contribution. Thank you. And yes, PNAR and nonlinear plus on NAR, you know, we should definitely try those out and work with those. I mean, they're beautiful models, and you know, we really love them. And more than that, you actually have got some brilliant software to fit them as well, which is always fantastic. With the star type models, there's a lot of similarities there between GNAR and STAR, but we think there are some important differences as well, and particularly on the way in which they and we deal with the networks. There's most of theirs is tied to a very strong lattice structure, which we think just doesn't work well with the kind of, you know, aerial type data that we've got here. David, all good points as usual. Thank you very much for that. In our defense, first of all, I agree with you. There's more that we could get out of that data. I think the idea of looking at outliers is a brilliant one, because that probably is symptomatic of something not going well or going very well at some location. But on the other hand, in our defense, you know, the fact that there is a simple model which does such a good job is actually very useful, and you could talk to medics about that, and they might be interested in knowing that. You know, if you're in that kind of environment, where are things going? Also, if you're some poor soul in the NHS charged with mechanical bed ventilation, bed planning, or something like that, then having something that forecasts well, you know, hours, or even the naive estimator, you know, that could be useful for them there. So I think there is some use there. On the question of random networks from Professor Sekar, that's a very interesting question. I mean, one thing about networks is that for any number of nodes, there are so many darn networks that you can use. I mean, it's just unbelievable. It's scary. And then thinking of the thing as a random graph problem is very interesting. I can advertise some work done with Henry, who's in the audience somewhere, where we've done some forecasting based on random networks and getting some really nice performance there. Steve, thank you very much. Nice point about the oh yes, it was the regional thing. Of course, Scotland, Wales, and Ireland. That's a very good point. one thing that we would love, you know, we have ONS, we have UXA, these are UK-wide things, but still we collect things like this on a, so the real fix will be, can we collect our data a bit more and in a bit more of a harmonized way? But we thought very quickly about that, and you have a suggestion which we'd like to hear about, but we thought about possibly you'd want to weight the weights a little bit more differently, you know, on the boundaries or something like that. And it's the kind of first reaction to that. And I think also finally on the transmissibility parameters of the virus, we were very careful in the variable we chose here, and we wanted to steer away from numbers of COVID cases or confirmed testing. I mean, there's about 100 different, slightly different variants depending on which country you're in about what. And the reason for that is, first of all, I think those, I'm probably going to get told off by medics now, but you know, you get confused between what's COVID like, what's influenza, and you know, there's all kinds of other things going on as well. The thing about mechanical ventilation beds is you have to be really sick to go in there, and it's kind of obvious is the wrong word, but to a doctor, my guess is they know when you need to go in to mechanical ventilation bed. So it's a kind of a again, I'm not probably using the right words, but it's a more certain variable to track. But it is certainly a few steps removed from the actual virus, how it's evolving and going around. So it's almost like a shadow of what's really happening in the country. So it's a useful thing to model from our point of view. Whether you could then somehow work back and get some information on virus parameters, I'm not so sure. The other thing about the transmissibility parameters is that there's probably about 10 groups in this country, all with each 10 different models, and giving the government 100 different possibilities. And we can't really compete with that, because there is a lot of specialized models for doing these things in epidemiology, which we're not trying to really compete with. But anyway, overall, thank you very much. Honored that you would come and listen to our paper, and thank you very much for all the contributions, which have all been brilliant. So yeah, thanks.
Very much, Guy. And just to add that a more considered reply will be given later in the journal with the paper. Okay, so information about the next discussion meeting. So the next meeting is at the RSS conference in Edinburgh. I would hope you would all be able to attend. So this will be on the 2nd of September. It will feature the Series B paper, Augmented Balancing Weights as Linear Regression by Bruns Smith et al. Full details of all upcoming discussion meetings are available on the RSS website, and they are announced in members' newsletters and on social media. If you would like to receive an invitation to future discussion meetings, please email journal@rss.org.uk and we'll add you to our discussant mailing list. For the ones that are in the room, thanks everyone for coming, and the ones online as well. But for those ones here, we will have a reception, a drinking reception. So this will be in the common room, room 549 on the 5th floor. Thank you very much.